carboxylic acids chapter today. There's not much to it. We kind of revisited the derivatives chapter, which is substantially larger. Just a couple of sort of housekeeping notes. The Unit 4 assignment sheet will be up on D2L this afternoon. I just need to put in some of the assignments when they're due. And then the lab you're going to start on Wednesday is a Fischer esterification that we actually do in a microwave. So you're going to be microwaving your reaction. And it's solvent-free, which is the nice thing. And another really nice thing is the reaction occurs with like no byproducts at all. So you do the reaction, you extract your ester, you don't have to purify it, you don't have to do anything, you evaporate the solvent, and there it is. And then we do ionize things. So what we are going to do is everybody is going to have a different alcohol to do the experiment. Not everybody, but we have a choice of like 7 of them, 7 or 8. And so I'm going to sort of randomly assign them to you. So to write your pre-lab, you'll want to write it for the correct alcohol. And so go on to D2L and look in that notes section, the thing that first pops up where I write you messages. And I'll put a little attachment that will let you guys can look at it and figure out which alcohol you'll be using in the experiment. Okay? All right, so here we go with carboxylic acids. We'll start off with the easy thing, and that is nomenclature. And to illustrate what's going on, we'll name that thing right there. They're really nice to name because if you look at your priority list, carboxylic acid functional group is at the top, so it always wins. And the carbon is always number 1. So you don't have to think about who's the parent, and you don't have to think about how to number it. So it's really nice that way. So the first thing you do is select the longest chain, and what you want to do is get the longest chain with the most functional groups that you can. So if you have some choices, go with the chain that has the functional groups. So in this particular case, we're going to be going across like that. That's not too hard to decide to do that. Okay.
You said there's most functional groups.
Right.
But what if there's a branch that has a functional group that has a higher than the other ones?
Then you would go down. We're going to do an example of that in just a minute where there's a branch. Let's say I had a branch and off the branch I had, say, a ketone and an alcohol, but the branch is shorter. I would go the branch because it has more functional groups. You want the most functional groups possible. And then if you have a choice between, I guess, let's say they're the same length, both have one functional group, priority would then take over. Okay, you're going to count the number of carbon atoms in the chain, and the parent is, of course, named based on that. Simple IUPAC type stuff. So this is, I don't know where to see that right here. You see the red? Is that too dark? No. Okay, it's a little easier to see. So it is 8 carbons, so it's going to be an octane parent. What you do to name it is you take the octane name, so octane. We're going to drop the E so that it becomes octan and add oic acid. And so it will be, the parent will be octanoic acid. And then what you do is you just go along and start putting your functional or your substituents on along with their numbers. So, like I mentioned before, the carboxylic acid is number 1, that carbon, and so everything else is numbered relative to that. So this guy comes out to be, when you go through it all, there's an ethyl at 4, hydroxy at 5, methyl at 6, and you just alphabetize those, and there's your name. So the only difference between this and, say, aldehydes is the ending. It's octanoic acid. Okay, questions about that one? All right, there's that one right there. Now this sort of presents to to us a couple choices. I have a long chain that encompasses a double bond and an H2 carbon with an amine on it. Or I have a shorter chain that has an aldehyde. And the rule of thumb is you do the longest chain with the most functional groups. So what we're going to do here is the one that's there in purple. So we start with the carboxylic acid, come down, and go across to get the alkene and the amine. That means our aldehyde is a substituent. And we addressed this a while ago, probably about a month ago or so. When you have an aldehyde as a substituent, what is that unit called, that C double bond OH? Do you remember what it's called? When it was a ketone, it was an oxo, right? It's a formal, yeah, F-O-R-M-Y-L. It's a formal group. So to name this guy, we're going to start out number 1 right up there. So 2, 3, a bromo at 4, formal at 5, 6, 7, and amino at 8. And then you just alphabetize that all. The only difference with this one is we had to deal with that double bond. The same way that we kind of did with a ketone or an aldehyde is it's built into the actual parent stem name. So instead of its 9 carbons, instead of being nonanoic acid, N-O-N-A-N, like it'd be an alkane, this is an alkene, so it's non-enoic acid. Okay, questions on that one? All right. Then the rings. I just hate rings. The cycloalkene rings, they just have named them very oddly in IUPAC nomenclature. So if it's on a ring, it's going to be weird. And we're going to name the ring as a cycloalkane. So in this case, it would be cyclohexane. And then you tack on to the very end of it carboxylic acid. So it's cyclohexane, carboxylic acid. All one big old long thing with a space where acid is. It's just weird. The point of attachment of that carboxylic acid, so this spot right here, this point of attachment is number 1. And then you just have to decide if you're going to go clockwise or counterclockwise to get the numbers as small as possible. So in this particular one, I think it makes better sense to go counterclockwise, go up towards that first branch, that CH3. And then you just number them, and you put your substituents on alphabetically, cyclohexane carboxylic acid. So this thing becomes, where are the methyls? 2, 2, 4, right? So it's 2, 4, dimethyl, cyclohexane carboxylic acid.
So, like, is it the first branch that you get to that?
Yeah, you want to number towards your first branch. Yeah.
It would have a double bond in the ring.
Then it would be, you would number towards the double bond to keep it small, and then it would be cyclohex 3-ene carboxylic acid, like that. Okay, any more questions on rings? All right, now, this is a list of kind of common carboxylic acids that a lot of them are found in nature. And it's, the structure is given to you, and it just builds. It's 1 carbon, 2 carbons, 3 carbons, on and on it goes. Sometimes, and this will even happen, I'll go into the stockroom, and I will want octadecanoic acid. And on the shelf, it's stearic acid. So these acids have really long-standing, accepted common names, which is kind of a pain in the neck. And so what's here on this list is the common name right here, like acetic acid. no one ever really says ethanoic acid, right? That's kind of geeky. So the first two, formic and acetic, pretty common. Propionic acid, maybe if you're really old, people say that. Now we've switched over, kind of right here is the cutoff where you start to go IUPAC. Right there. Don't say ethanoic acid, say CA. But propanoic acid, that's like normal, that's okay. Butanoic acid, all that. So these are the IUPACs, you can never go wrong. Ethanoic acid isn't wrong. People would just look at you like, really? Okay, so probably don't want to do that. The smell is right here. They really start to smell bad. Down here where they're really getting big, these are fatty acids, which means just a long carbon chain. And they don't smell so bad because they're big, and so they don't tend to have many molecules in the vapor. They have very, very low vapor pressure. And so they don't smell. But the ones that are up in here, they stink. Like you guys are all familiar with acetic acid, that smell that our lab fills up with. It's a vinegar smell that gets pretty strong. Notice down here though what's happening. Goat odor, goat milk. Dirty socks are an unclean goat. For those of you that have goats, I guess unclean goats and clean goats smell a little different. So an unclean goat. Rancid butter, very, very nice. A lot of these smell really bad, and the smell lasts and lasts and lasts. I had in a toolbox that I inherited from the person I was hired to replace, so this was like 18 years ago, I inherited this toolbox. And somebody, as a joke, had put some butanoic acid into it. And for about, it's gone now, but for about 10 years, I would take the toolbox outside to open it. Because you'd open it in lab and everyone would go, oh! It was terrible. So these things really, really stink. And in a stock room, you can kind of tell when you're in the carboxylic acids aisle, because you walk down it and it sort of smells like an unclean goat. It's just, if you know you're there. There is a mnemonic for the fatty acids. So that's these ones, right down in here. Capric, lauric, myristic, all those. There's a mnemonic. Chemists love to make people suffer. And if you take a look, whoop, chemists love to make people suffer. Right there, it's for the fatty acids. So if you ever go into biochem, just remember that. It'll help you memorize it. There are also diacids that are fairly common, especially in biochem. And we're going to name them very IUPAC-y. What we're going to do is count the number of carbons and then give it the parent F, pro, but, like that, based on the number of carbons. And then we are going to, so let's say like 3 of them. 1, 2, 3, that's based on propane. We're going to go propane, dioic acid. That's how they're named, dioic acid. So if there were 5 carbons in the chain, right here, it would be pentane dioic acid. So naming them IUPAC is very easy. But if you go on, you'll have to be familiar with the common names. I won't test you on them because I don't know them. I have to actually go look them up. But some of you will be forced to memorize these when you go to biochem. These are the common names right here. And there's another mnemonic that's been developed to help you remember them. And it's, oh my, such good apple pie. And it goes down through the first, up to 7 carbons long. Oh my, such good apple pie. Yes?
Are they always symmetrical?
Yeah, they're always going to be at the end. Okay? All right. I will not test you on common names, because I don't want to have to go look them up. Okay, as far as carboxylic acids, you guys probably remember in the IR, the OH stretch was huge. And alcohol is kind of a loopy thing, very obvious, around 3,300. But the carboxylic acids just kind of troweled from 3,500 to 2,500 in this giant smear of lowness, sort of. It wasn't anything really defined. And what's going on with those is they have really extensive hydrogen bonding. And up here's this thing called a dimer. that's showing that extensive hydrogen bonding. On one carboxylic acid, you have both an OH right here, and that can hydrogen bond. And it can form, its hydrogen can bond to the oxygen of another carboxylic acid, so you form a hydrogen bond right there. But you have an oxygen up here that can accept the hydrogen bond on that same carboxylic acid. So you have a donor here and an acceptor there. And this one can accept the hydrogen bond from another one. So they can get locked into this little, the two of them together, this little system where one's donating to one and the other one is accepting the hydrogen bond from the one that's donating on the top. So you get this little two-unit system that is called a dimer. And that's why the IR has such a big, wide stretch, is because of that hydrogen bonding. Another thing that it affected, I don't think that we talk about it here, it's sort of trivia, that this dimer is actually a fairly strong unit. And when people were doing molecular weight determinations, it caused carboxylic acids for the mass of a mole of pieces to come out twice what the molar mass was of a carboxylic acid, because the mole was actually a mole of dimers. And so a dimer weighs twice as much as a carboxylic acid. So it messes up molecular weight determinations too. Because of all this hydrogen bonding, carboxylic acids have really high boiling points, which is good for us because otherwise they really smell really bad. So you can see that we have, start with an aldehyde. The aldehyde cannot hydrogen bond, and it has a boiling point of 49. Then when you move to something that can hydrogen bond in one place, about the same mass, the hydrogen or the boiling point jumps up. Obviously, because you have one hydrogen bonding interaction, it's 97. Then you go to a carboxylic acid, roughly about the same mass, and the boiling point jumps to 118 because it can hydrogen bond in two places instead of just one. Okay, they're going to be water soluble because of the hydrogen bonding, and it's going to be the usual 4-to-1 rule that we've seen with alcohols, with amines, and we'll see it with these as well. You have one carboxylic acid unit, you can have a 4-carbon long chain, and it will be soluble. Once you start getting more than 4, solubility gets less and less because it becomes this chain becomes more alkane-like, and the carboxylic acid N isn't enough to drag the entire thing in. Okay.
Are you counting the carbon that's part of the carbon?
Yeah. Okay. And this is just showing the IR that I was talking about. An alcohol, they're really obvious. You have this really nice OH right here. Carboxylic acids are much more blocky and spread out. This is one up here, the top one. You wish yours looked that good. Okay, they almost never do. They kind of go, you guys have all seen them, they go, bleh, bleh, and just kind of this, it's like a depression sort of thing, and you almost look at it and say, is that really a peak or not? You know, just really kind of spread out. Blah. Okay, as you can probably guess, carboxylic acids are acidic. So they can lose the hydrogen that's on the oxygen, and they form this species right here called a carboxylate ion. So acetic acid would form an acetate ion. The pKa is 4.82 for, what's this, butanoic acid. That's not huge. You know, when you guys were in Chem 400 and 401, that is not really tremendously acidic. On the OChem scale of things, though, that's wonderful. That's super, for us, that's super acidic. It's the most acidic organic thing we're going to run into. So they're, as far as we are concerned, pretty darn acidic on our scale. The typical factors that have affected acidity and basicity will also affect carboxylic acids. So the first one would be if you have an electron withdrawing group nearby. You can get, let's go to the board for this. You get the inductive effect when this happens. So if I have, and what are we looking at? 4 carbons. So I'm really looking at how I'm going to be stabilizing this carboxylate ion. The pKa for it was 4.82. And what's helping to stabilize it is, of course, resonance. Right? That definitely causes everything to be a little more acidic. But there's nothing special going on here that can also withdraw electrons towards it. When you put on, though, the chlorine close by, because the inductive effect is distance related. When you put it on close by, this is pretty electronegative. So what it does is it withdraws electron density towards itself. That means this carbon is now electron poor. It's had some electrons pulled away from it. It's got a delta plus. So it in turn is looking for electrons. And so it sees this big delta minus over here, and it starts to pull towards itself. And what that does is it spreads out the negative charge. And that is just the inductive effect. It's not that powerful, but it helps a little bit. That's it through sigma bonds. It's definitely not as strong as the resonance effect, but it does matter. And it's distance related. So you can see when the chlorine's as close as you can get it, it did take the pKa and trumped it fairly substantially. When you put the chlorine no further away, that effect does not spread out very well over a bunch of carbons. And this pKa, it helped a tiny, tiny bit, but it's not like it's a super strong acid now compared to what it was without the chlorine. Because the chlorine is so far away, it almost doesn't matter.
And if it's on beta carbon?
It would be slightly stronger acid.
Okay.
Yeah. So if it were here in the middle, it's not as good as having it there, but it's going to be better than having it there.
And if it's
If you went out even further, it's not there. It's just too far. I almost consider one line alpha carbon important, beta carbon, anything beyond that, whatever. You know, it's just getting too far away.
for everything?
For just about everything, yeah. Okay. You're guaranteed on some standardized test in your life to see a problem like this. And there was an ACS version that we took. They had no fewer than, I think, 70 test questions total, right, on what's going to be your final. I think 4 of them were devoted to problems like this, acids or bases on benzene rings, which is a huge percentage. It was ridiculous. But you're guaranteed to see one of these. And what you're looking at there is, again, the effect of groups. Well, look at the stability of this guy. The effect of group Y on getting this negative charge delocalized. What we need to do to make it more stable, it's more stable if that negative charge is delocalized. Now, what kind of group down here is going to help pull electron density into the ring and off of the carboxylic? Electron withdrawing groups, good. They will help to stabilize the negative charge. If it's an electron donating group, what do you think that's going to do? Yeah, it's going to make it worse. Because if it's an electron donating group, then I've got something feeding electrons in. That means the benzene ring is not as likely to pull that electron out again. So, with that in mind, let's do this problem right here. Okay. As far as the situation's going here, I have just a cyclohexane. Okay, so there's not much going on there at all with a benzene ring doing anything with it. And then we have benzene rings, the other three, with different kinds of groups on there. So, as far as the numbers, what would you guess is going to be the one that is the most acidic of those three? What would you guess is the most acidic? And fix a typo, by the way, I just noted on mine. I keep obviously needing to fix a note. Instead of a diacid, which change that into an aldehyde. It should be an aldehyde. The number I have is for an aldehyde. So scratch that out and make it an aldehyde. Okay, so which one were we guessing the most acidic?
Far right.
Yeah, I've got a little, once you make this an aldehyde, that's an electron withdrawing group. It's going to be pulling electron density out of the ring. This is the 3.75. 3.75. Which one would you guess is going to be the worst of the three? Yeah, the cyclohexane is, because you don't have any resonance structures. The benzene ring is somewhat electron withdrawing, and the cyclohexane doesn't have that. And so the number that corresponds to a benzene, cyclohexane carboxylic acid, is the 4.9. That's the 4.9. So we've got the two extremes. So that leaves us with 4.55 and 4.36. So what do you think is better to have in terms of acidity? A CH3 on there or an OH on there?
CH3.
Yeah, the CH3 is not as good a donor. It's an inductive donor. It's pretty weak. And so that won't be as bad for the acidity as an OH. And so the CH3 is the 4.36. There's your 4.36. And a little worse, the 4.55 is that. It sounds from your answers like you guys are all pretty comfortable with this. Okay. All right. This next part is almost all review. That's preparing them. You guys already know how to do this. First thing you can do is oxidize a primary alcohol with just about anything but not DCC. So everyone's got that down. This is not as common, but some people were doing it on the homeworks and things. You can take an alkene and oxidatively cleave it with hot KMNO4, and that's going to give you potentially mixed products. This particular example I'm using, one side of the alkene is disubstituted, and that's the side right here. So when I cleave, it's going to just turn into a ketone. The other side, monosubstituted, that can get all the way oxidized to a carboxylic acid. So the parts that become carboxylic acids are only the monosubstituted halves. The third one contains just benzene. We've used this quite a bit too. You can have an alkyl chain off your benzene, and if you hit it with hot KMNO4, then you can cleave it off to benzoic acid. One thing to remember is you have to have at least one hydrogen in the benzoic position. So if this were, say, a tert-butyl group and it was all carbons on the benzoic carbon, this wouldn't work. You have to have at least one hydrogen. So far, these are all review. This next one, that's the one we talked about last week, that you're going to really wish you'd known this like last semester, a lot earlier. It is taking a Grignard and putting CO2 in to form a carboxylic acid. This really is a Grignard reagent, and it's attacking a C double bond O. The difference is the structure of the carbon dioxide makes that C double bond O still retain one carbonyl. So what's going on with this? Your Grignard attacks the carbon of the carbonyl, just like if it attacked a ketone or an aldehyde. electrons get pushed out onto the oxygen. Same exact thing we did. So you end up with the carbon attached to what was the carbonyl, and there's your O minus. The only difference is, when it was a ketone or an aldehyde, this right here was an R group, right? But now, it still is a C double bond O. So when you put CO2 in, kind of riding along unaffected is a C double bond O. What that means is once you protonate, you have a carboxylic acid. So it's the exact same reaction, but there's no R group on the carbonyl. So it's really handy for adding one carbon. That's all it can do. It's just add one carbon. Okay. And then this one, we learned about this when we were doing the diazonium compounds. You can take a nitrile, the C triple bond N. On this particular case, I have it on a cyclohexane. It could be on a benzene, it could be on anything. If you can build a nitrile, this works. So you need your C triple bond N. You can treat it with either H plus H2O and heat. And I think that's the one I gave you guys. Okay. Or you can also do base water and heat. So if you have something that is going to blow apart when you use acid, you can use base if you wanted to. And when you do what's called the hydrolysis of this, you end up forming a carboxylic acid. And we're going to steer clear of the mechanism for right now. When we go and do the next chapter, which is the derivatives, we're going to spend a long time looking at nitriles, and we'll do all their mechanisms all at once. Okay, so for now, just put a note saying mechanism later, and we'll talk about it probably next week. Okay, so far so good? Okay, must be strong hot. All right, and that's that. I want one of these in my house.
Like you said, you have.
Look at that. I could do that all day, I think. You guys notice there's a little door that closes? Okay, I'm gonna get this stuff put away before I lose track of it at the end. All right, so now what we're going to do, spend the rest of the day focusing on reactions of carboxylic acids. Probably finish them. Okay, so the first one's kind of a no-brainer one, but we're going to see why it's important in just a couple minutes. So this is all under reactions. And this first one seems stupid, but deprotonation. So we're going to use the fact that that hydrogen on the oxygen is acidic and pull it off. So let's say we had cyclohexane carboxylic acid. And I want to make the carboxylate ion. I could just put it into water and let it dissociate, but it's a weak acid. And so what, if I were to do that just in water, there's going to be an equilibrium. And in plain water, I would have some of that, some of the carboxylate. And I would also have some of just the carboxylic acid. And since it's weak, I'm going to have a lot more of the carboxylic acid than I am the carboxylate. So if I wanted the carboxylate ion to actually do anything with, this isn't really effective. So what we're going to do is to make a lot of this to drive the reaction forward, add a base. So if I want a lot of the carboxylate, like 100%, because it's going to be an intermediate to do something with, all I have to do is add some base. And then, for all intents and purposes, I'm looking at getting pretty much 100%. Now, as far as the utility of this, why would you want to? So this is usefulness of this guy. Well, the first thing is it can be a nucleophile. So I can use this O- to go off and attack things. And we're going to see in the next reaction that we're going to be making esters this way. It's one of the ways to make an ester. So in that respect, it's pretty useful. Another thing it's really useful for is in lab. It will remove the old goat smell from glassware, from you, wherever it is. So this, I actually use this in my lab quite a bit. You do a reaction with a carboxylic acid. It smells bad. And so you wash your glassware with soap and water. You wash your hands with soap and water. And no matter what you do, the carboxylic acid, if it's very long, is in water soluble, right? So you can't really get all of it off. And your nose is really sensitive to it. So you might have glassware that smells like an old goat. You might smell like an old goat because it's on your hands. So what you can do is you take, let's say it's on a beaker. So you have this beaker, and adhere to the beaker is a trace of carboxylic acid. So your glassware stinks. What you do is wash it with dilute OH-. It doesn't take much. That will convert the trace of carboxylic acid to the carboxylate. It deprotonates it. What can you tell me about this? It's now a salt. What about that salt? It's water soluble. Yeah. And so then it goes down the drain. It reduces the smell. So it's a really common trick to get rid of stink smell on your glassware. You know, kind of in line with that, I've also had glassware where I had amines adhering to the glassware. You know, they just kind of smells a little bit ormy. And remember, amines smelled like rotting fish, or remember cadaverine, putrescine. You really don't want this on you. And so if you have an amine stuck to your glassware, so say you are contaminated with cadaverine, what can you do to get rid of the amine and make it water soluble? You put some acid in, exactly. So you can take that, dilute H+, protonate it, and now it's water soluble. And you could do it that way. Okay, same kind of principle. We're most interested in the use for A, making esters with it. So, let's go ahead, and that can be reaction 2. Use a carboxylate ion to make an ester. So, let's say we made benzoic acid. We can deprotonate it. NaOH to make benzoate, it would be sodium benzoate. And now, the next reaction I'm gonna do is an SN2 reaction. So this guy is the nucleophile, right here. Here's my nucleophile. And it's gonna participate in an SN2 reaction. And I'm going to add an alkyl halide to it. So let's add, I don't know, ethyl bromide. This only works well if your alkyl halide is primary. You get tertiary, certainly won't work. Secondary is it's not so great because it's not the world's strongest nucleophile. So it works really well with just primary ones. And so what will happen is the O- will do backside attack, kick out the bromine, and you will have added the 2 carbon chain. You've made an ester. It has kind of limited utility because you can only use a primary alkyl halide. Questions on that? Okay, let's say you wanted an ester that was a little more complicated. Let's say I didn't want just the primary alkyl halide on there, but let's say I wanted something like, I don't know, a second butyl group. Say I wanted something like this. Like that. Since this is now branched, I cannot do this. I can't do that. That's not going to be effective. And so I've got to have a different way, something a little more general. And that reaction is what we'll call number 3. It's really famous. Fisher, who was a very busy guy with his Fisher projections. Fisher esterification. This is a really useful reaction. Your R group that you're going to put on the ester can be primary, can be secondary. The book says it can't be tertiary, and I didn't really believe them. So the reaction we're doing on Wednesday is this reaction. I had a couple people in the class actually try it with the tertiary. It didn't work, so it's true. So it can be primary or secondary. And what we'll do is we'll put up a generic reaction, and then we'll do a mechanism with a specific molecule. So a generic reaction, you take a carboxylic acid. The R group can be anything, just a carboxylic acid. You add to it an alcohol. This R group can be primary, secondary, not tertiary, so it won't work. You add an acid catalyst. And to differentiate the 2 R groups, put a prime on that one. So we know they're different. Yeah? Hindered secondary probably won't work either. I never tried that one, but I know unhindered secondary is okay. And what you're going to end up with is R, C, double bond O. So that's this portion. Okay? And then attached to it is O, R, prime. That is that portion. Now, I've left something off. I lost an OH on the carboxylic acid and an H on the alcohol. What do you think my other product is?
Water.
Water. And this is an equilibrium. So we'll have to talk about some of the things we can do to push it to go to products. Okay, so it's carboxylic acid and an alcohol with an acid catalyst to make water and the ester. All right, let's do a mechanism. And for the mechanism, So in these kinds of mechanisms, and we're gonna see this is true with the derivatives as well, that when we have a nucleophile, kind of in general, we have a C, double bond O, and whatever's on there. And we saw this with ketones and aldehydes. You add something that can be a nucleophile, like the alcohol. The nucleophile will attack at the carbonyl. We saw that before, we've seen it a lot. And you end up having electrons go up onto the oxygen. We have O minus and now, when we were dealing with ketones and aldehydes, let's say it was a ketone. So we'll put a C and C there, C and C. With a ketone, this tetrahedral intermediate that we had, I could never reform my carbonyl, which is that C double bond O is a pretty strong favorable bond. But I couldn't reform it and like kick off a carbon. I couldn't kick off the side chain of my ketone, right? I couldn't kick off the H of my aldehyde. And so with a ketone or an aldehyde, I was stuck here. But take a look at what happens when you have a carboxylic acid. Here's my nucleophile. It attacks. Electrons go up. I get a tetrahedral intermediate. There is a difference now with what's going on. Right here is a potential leaving group. It's not a good one. We told you we can't leave. You're going to find out we kind of lied a little bit. But as it is, that would be preferable not to leave. If I could turn it into water, it would leave, right? So there is a potential leaving group here. And we're going to see with the derivatives that the difference in what we're going to see over the next 2 weeks is there is a leaving group. So I can reform the carbonyl and spit out my leaving group. I may or may not have to play around with it to get it to leave. Okay, but the potential is there to kick it out. And we're going to see that mechanism play out here. So, back to our example. I have a 4 nucleophile. It's going to count on the delta plus of that carbon that it has to attack. The problem is that this carbon has electrons withdrawn from it by the C double bond O, just like a ketone or an aldehyde. But to make up for it, very conveniently, I could have those electrons kind of feed into it to help that out, right? So right now, the delta plus here is pretty small. It's not spectacular. So I've got really an electrophile, that carbon with the delta plus, that's crummy. I've got a crummy nucleophile. This reaction's not going to go very well. What should I do first? We did it with ketones and aldehydes too. How about to make this a larger delta plus? What should I do? That's where the H plus comes in. The first step we're going to do is we're going to carbonate. So I go double bond OH plus OH. And what that does is it makes this a much more polar bond, and I have a larger delta plus now. And then my alcohol can attack. So it comes in, it attacks. Electrons go up onto the oxygen that had the plus charge on it. I have C, OH, OH. I have a tetrahedral intermediate that looks like that. And now here's the key thing. Reforming the C double bond O is favorable. And now, for the first time, we're at a functional group where we can do that. If I could bring these electrons down, back down, I could kick that guy out and reform my C double bond. The only problem is it's a terrible leaving group. So, I'm not going to do it right now. What can I do to make it better? I can protonate it. And very conveniently, I need to deprotonate right there, right? So I can deprotonate and protonate. So I'm going to do the minus H plus plus H plus that we talked about before. Is everyone comfortable with that? Okay. So now I have OH2 plus, and this is a good leading group. So now we're about done. I can reform my carbonyl and kick out water. And the last step is just the minus H plus. I've got to get the carbonyl freed up.
Does it just like fall off or does the water take it off?
There's not a whole lot of water in there. Probably an alcohol grabs it. Something grabs it. And so you've got yourself an ester. Okay, any questions about the mechanism? Was it truly catalyzed? Remember, if it's catalyzed, we used H plus, and then we got H plus back at the end. So there was a lot of H plus movement, so let's just check. Here I put it in. Right there I lost it. Here, I got it back, but then promptly it got flipped back in again. So that didn't help at all. Here, I got it back. So the net result is that I never used up that H plus. I put it on, it switched all around, and then I got it back at the end. So it is truly acid catalyzed. Now it's all equilibrium steps. So we are going to have to do something to push it to products. What are some ideas that we could do to make it go forward, actually? We could remove water. Remove water as it forms. And we talked about ways to do that. Put a drying agent in. Put in those little pieces of ceramic called molecular sieves. Remember the Dean Stark trap we talked about? With the benzene azeotrope and that weird piece of glassware? There's a lot of ways to remove water. What else could we do? How about excess acid? Carboxylic acid, to be a little more specific. Take one of your starting materials and use it in excess. You can do the carboxylic acid, if that's the best option, or excess alcohol. And the choice really depends on which one you want to waste. If you had built, say you had this carboxylic acid, it took you 6 months to make, it's got like 5 chiral centers, and this, that, and the other. Are you going to use excess of it? Just throw whatever is left over down the drain? No, that would not be your choice. You'd want to use excess alcohol, right? If your alcohol were hard to come by, don't use it in excess, use the carboxylic acid. What we're going to do on Wednesday is we're using acetic acid, and that will be our excess reagent, is the acetic acid. It's also easier if you have excess carboxylic acid, you can get rid of it by just washing things with base. You can turn it into carboxylate salt. So this is often the best choice, if it makes sense. But if it were some super specialized carboxylic acid, you'd never use the excess. Okay? So far so good? Alright. So that's the reaction you guys are going to see in real life on Wednesday. Now another one, we've used this one a lot, but I don't think we've ever done this mechanism. chloride, pyridine, and you get to an acid chloride. We've done a lot of things with that. We used to do Frito crafts with it. We made amides with it. We did one other thing, I can't remember what with it. We've made acid chlorides a lot, but we've never actually looked at how it happened. So the time has come to take a look at that. So let's do a mechanism. And we'll do an R group, keep it easy on us. So there's your carboxylic acid. Thiamyochloride looks like this. Pyridine looks like a benzene with a nitrogen in it. And we've added it to a number of things, and it always had the same purpose. What did pyridine do? It's a base. Yeah, it's a base. So it's a non-nucleophilic base. I don't want to use OH minus, because if I do that, then the OH minus can go and attack things, and I don't want that. So it's a non-nucleophilic base. So what's going to happen is the oxygen lone pair electrons attack the sulfur. And the easiest bond to break is not the sigma bond between the sulfur and the chlorine. The easiest one to break is the pi bond. And so what happens, it's very carbonyl-like. Electrons get pushed up onto the oxygen, exactly like if this were a ketone or something. So I have an SO minus 2 bonds. And now I have a couple choices in what I can do. Let's first get rid of the H plus on the oxygen, okay? And then we'll fool around with sulfur. We'll do 2 different steps. So the first step we'll do is we'll go minus H plus on the oxygen. So pyridine, which is my base, will grab that hydrogen. And I will have, let's move over here with it. Double bond O, 2 and O, OH on L, and that strange thing going on the sulfur. Now, if we could reform the S double bond O, things that are double bonds, pretty strong bonds, so we're going to do that. I can bring the electrons down, reform my sulfur oxygen double bond, and I've got a leaving group there that I don't even have to do anything to get it to leave. It pops off the Cl minus. Then I have that plus Cl minus. We're halfway through. That doesn't look anything like the acid chloride. But I have done something important. At this point, 2 important things. The first thing is, I have a chlorine that can function as a nucleophile. And the second thing is, I have taken an OH from the carboxylic acid and converted it into this. Why might that be important? It's a good leading group, exactly. So this guy can be a leading group. When I kick off an O minus here, it can be demobilized into that sulfur. So it's a good leading group. Very similar to, remember tosylates we talked about last semester? Similar to those. So, let's go to phase 2. My Cl minus nucleophile attacks the carbon. Electrons go up onto the oxygen. Now this thing. And it turns out, we actually don't care about this sulfur chlorine thing. This actually falls apart. It's not tremendously stable. And you get byproducts, but we don't care about it. So no one ever even writes that out. There it is. So it's kind of a long, complicated mechanism that we just sort of poof, get an acid chloride. It works really, really well. We're going to be doing it when we make off. In about 2 weeks, we're going to make the insect repellent off. And we are actually going to use the chloride and pyridine on a carboxylic acid to make the acid chloride. Okay? Any questions? All right. Now, as far as what this acid chloride can do, we'll save that for the next chapter. We're going to spend probably a good 45 minutes talking about the chemistry of these guys. They're really important intermediates. But for now, all we have to do is make them. All right. And our next reaction. Now let's throw this one in. This would be number 5, I think. This is one, it's not very important to us synthetically, it's very limited, but someone did come back. For a while I didn't even talk about it, and then someone came back when I had talked about it. It was on their MCAT, of all things, this craziness. So this is a carboxylic acid. Take a carboxylic acid, you treat it with something called diazomethane, which is CH2N2. And you form only that. That's the only thing you can ever make, is to put a CH3 on there. It's an ester, and it's only a methyl ester. Only. Super limited. So we could do this pretty easily with the carboxylate ion and CH3I, right? Or a Fischer esterification would do it great. Or this. The only problem with this, that's why it's not so common, is diazomethane is toxic and explosive. So there are a lot better ways to do this reaction that we've just learned. But there it is. Let's go ahead and see if I even have the mechanism for you guys. Here it is, right here. It's kind of an interesting mechanism. Let's go ahead and do it. I won't ask you this mechanism. I don't think this reaction is very important.
Did the person get it right?
I think they did. I think so. It was one of these recognition type reactions. It's not the most common thing. So, diazomethane. Let's go ahead and fool around a little bit with its Lewis structure first. It is CH2, double bond in, double bond in. Middle nitrogen has a plus, the end nitrogen has a minus. Okay, so what we are going to do now is kind of redraw the resonance structure. So I'm going to put CH2 minus, single bond to the nitrogen, triple bond to the nitrogen, still a plus in the center. Just a different resonance structure. And this mechanism is kind of neat. So we take this guy, this is the important one, right here. And we're going to treat a carboxylic acid with it. So the first thing that happens when I mix the two together, CH2 minus, that's pretty basic. And I just happen to have an acid present. So the first thing that happens is an acid-base reaction. We have that. Now say you confront this on an MCAT or something. Look at that and tell me what's going to happen next.
I was gonna attack the CH and kick off
Yep, the O minus is going to attack that CH3, and what's it going to kick out?
the nitrogen gas.
Nitrogen gas, good. Attacks the CH3, nitrogen gas is kicked out, and you end up with a methyl ester. So it's a kind of a neat reaction. It's very efficient to form a methyl ester. But given its potential safety issues and its limitations, it's only methyl esters. It is not as common as the other things we looked at. Okay. The next one. This is one you'll get a lot of use. I think it's number 6 now. Reduction. When you reduce a carboxylic acid, well, reduction is the opposite of oxidation. What did I oxidize to get to a carboxylic acid? Primary alcohol, right? So when I reduce a carboxylic acid, guess what I make? A primary alcohol. So it's kind of this process running backwards is what it is. And to do this, we need a fairly good reducing agent. Something like sodium borohydride is just too weak. From now on out, for this whole unit, the reducing agent of choice is lithium aluminum hydride. It's good enough. Followed by H3O+. LAH is good enough to reduce any kind of carbonyl. Sodium borohydride is just not good enough. Okay. So let's go ahead and look at the mechanism, and then I'll give you some things that may help you out synthetically. Lithium aluminum hydride is a source of H minus. And what's going to happen is the H minus is going to attack the carbonyl, and electrons will go up onto the oxygen. Oops. There's OH. Okay. And now what do you have? This is something you're not going to like. Finally, there it is. We kick out the leaving group. It's not such a great leaving group. And we end up with that guy. What's going to help us out with this is that you don't actually isolate this. This is very reactive with LAH. And so it's not isolated. So you do pass through an aldehyde. So we can kind of change this a little bit. And we can say, oh, okay, you go through an aldehyde and then you go down to the carbonyl, or down to the primary alcohol. This guy's not isolated. Hydride attacks it, electrons go up. They cannot come back down and kick out H minus. That's not going to happen. So this is sits here and stops. And when you add H3O+, you have gotten to your alcohol. Okay? Now just as an aside, this is the mechanism seen in some books. In another book that I looked up, what they did was something a little, probably might make you a little happier. This is an alternate. What they did is they first created that. So the H minus did an acid-base reaction. Created this. The counter ion is lithium. This complex right here was really strong, a strong interaction. And that ended up being the leading group. Okay, to make the aldehyde. So H minus attacked, electrons went up, they came down, that was the leading group. Okay, either way you look at it, the leading group's not spectacular. You end up with an aldehyde though that immediately reacts, and that's what helps you. All right, we will call it quits there, I think. There's one more. I've got to decide if I want to tell you or not. It just depends. We may or may not look at it, but what we're going to do for sure next time is we'll be in derivatives. We may have like 2 minutes left in carboxylic acids. So there are derivative PowerPoints for the nomenclature in particular. So at least I think there are. There are. Come with them.